So let's start with your Rubik's Cube work, where you used reinforcement learning to solve the problem. Can you just tell us a little bit about the specific innovation that was involved and what you learned as a process of actually solving the problem? So what sort of interesting new insights did you get from doing that?
You can see the website of our Deep Cube. It's called Deep Cube, Rubik's Cube Solver, where you can scramble the cube and then ask the system to solve the cube for yourself. We're interested in the Rubik's Cube for a number of reasons. It's a problem that has a very large state space, something like 10 to the 19 possible states, and only one state is the solved state, the reward state. So it's like having a gigantic golf course that is completely flat with many possibilities and a tiny hole in a place that is difficult to find. And there are many problems that have those characteristics. And in addition, if you do random moves, like people have solved games like Go or chess with random moves, if you do random moves in a game like chess or Go, you will always finish, right? Somebody will win, even with random moves. If you do random moves on the Rubik's Cube, you will never solve the cube. So those are peculiar characteristics of this class of problems. There is many other problems that have the same characteristics. And so that's some of the reasons why we have worked on that and some of the related problems like Towers of Hanoi and Puzzle, etc. And it seems a little bit esoteric maybe to this audience, but a lot of problems in business, in robotics, in planning have the same characteristics. If you think about your kitchen, when it's a complete mess, if you start moving dishes randomly, you will not clean up the kitchen, right? So you need to plan and do things in a very organized way. And so this is a prototypical problem with those characteristics. And of course, you do reinforcement learning, and you have to start from the solved state and work your way back.
So talk a little bit more about that, because in many machine learning problems, there's sort of a natural gradient that gets you from your initial state to where you want to go. And you do some sort of gradient descent or stochastic gradient descent. But for these kinds of problems, like design problems, where you can be really close to the solution and not know it, there's no sort of natural notion of distance. How did you deal with that?
There is actually a natural notion of distance for the Rubik's Cube. How many moves are you away are you from the solved state, right? And for the Rubik's Cube, it's computable. There is a way of computing that. But basically, you have to start from the solved state and then scramble one time and learn how to solve one scramble. And then you scramble twice, and you learn how to solve those scrambles, and you keep doing that. So you have to create a sort of curriculum where you work your way backwards from the goal state, where the reward is, back to a completely scrambled state.
So, what else is going on in your lab that is similar, or different from this? And in the process, can you also maybe describe what reinforcement learning really means? Just in case people aren't familiar with it.
Just ask me 5 questions.
In 2 sentences, pick them in any order.
So what else is going on in our lab? Well, we work on broadly speaking, we work on the theory behind AI and deep learning, so theoretical questions. We're trying to think about how to build the next generation of AI systems that is more intelligent and more robust. And then we work on applications, because that's where we test our ideas. So Rubik's Cube and all kinds of other related puzzles are in this class. Another reason, by the way, to work on the Rubik's Cube is that it's very mathematical. And of course, we would like to develop AI that can do mathematics. We're very far from having achieved that, but that's one of the fundamental questions that are open in AI, how to deal with symbolic things rather than images or sounds, etc., which we know how to do quite well. We have applications in a variety of domains in the biomedical space, a lot of applications to biomedical imaging. We built a system that can automatically detect polyps in colonoscopies, in videos. It's being used in the UCI Medical Center for example. So a lot of biomedical imaging. We're also applying machine learning methods to genomic data, gene expression data, etc. What is reinforcement learning?
Yeah, so and to what extent are you using reinforcement learning versus other kinds of learning methods in these problems that you're describing?
We use a variety of methods. It depends on the problem. Typically, if you have, say, image classification, you will not use reinforcement learning. You will use typically convolutional neural networks for classification with, gradient descent. Reinforcement learning is used in situations where you have an environment and you have one or multiple agents that are acting in these environments, and they receive rewards, and they have to learn how to behave, how to take the right actions in order to maximize their rewards.
Okay, so if I hear you right, you're saying that the rewards may be, I guess, delayed relative to supervised learning, where you have sort of a label associated with every datum?
Exactly.
Okay. Tell me a little bit about, or rather tell us a little bit about the extent to which, and I'm sort of going to go a little bit general here, to what extent do you think there's sort of a hype about AI these days? And what I'm really going to get at is, have we really come close to solving some of the really important problems behind intelligence? Are we mistaking recognition for intelligence? I mean, I realize that recognition is a key aspect of intelligence, but where do you stand on that? Like how?
Well, there is no question that there's been a lot of progress in the last 10, 15 years. A lot has been driven by GPUs, by computing power, by availability of very large data sets on the internet, etc. So there has been a lot of progress, but we're very far from having solved AI in a general sense, Turing tests or things of that sort. Anyone can try to talk to Alexa and Siri and break it very easily. Right there you see where are the current limitations of AI. So we're very far from having machines that can do mathematics or write interesting poetry or novels or converse with us at a significantly advanced level.
Yeah, I was. It's funny you say that, because I was sitting there and I was reminded when in one of the previous sessions I must admit I checked my email, and one of my investors asked me, "Can you give me an attribution of your performance?" And I said, "Oh, the adaptive models are killing it, but the trend models are mixed." And then I forget who it was, said, "Oh, things like killing it is really hard to ambiguate or disambiguate, and that's kind of one of the hard things about language." In what ways is vision different from language in your estimation? To what extent do the same kinds of methods apply, and where do we run into difficulties in language with these kinds of methods?
Well, if you solve, they are essentially equivalent. I mean, solving vision would mean not just being able to classify images, right? Today we're very good at taking an image and deciding yes or no there is cancer, or yes or no there is a cat in that image. But that is not really understanding of visual scenes. If you had a full understanding of visual scenes, it would be essentially equivalent to being able to converse and to solve the Turing test.
That's interesting.
So in the same way, we have reasonably good models that can translate from English to Japanese, Google Translate, etc. They are reasonably good, but they are brittle. It's easy to break them.
Sure, they don't really understand anything.
They don't understand anything. Right. And the same thing, when you look at those images and you say cancer, no cancer, you don't really understand anything about cancer.
Sure. So this is an interesting segue into this whole notion of understanding, but even before understanding, explaining. To what extent do you think these connectionist architectures are capable of handling things like explanation? Are they limited primarily to recognition kinds of problems, or do you think they can actually handle explanation and introspection the way that humans do?
So that's a very good question, and a significant concern in the field. And when you deploy these solutions, engineers are very worried about explaining how does the system reach a certain conclusion, and how can we be sure that there is not a catastrophic failure somewhere in the system, right? So those are very important questions, and there is a lot of work that is being done on those questions. I would argue that one of the keys is using a very basic principle in engineering, which is encapsulation. You have to build systems that are modular so that you can track down into specific modules where the sources of the errors are. I'll give you an example. When we were working on the colonoscopy problem, we had cases where the system would say there is a polyp in the image, for instance, when there was no polyp, so a false positive, right? And we couldn't find out where was the source of the problem. Then we built a slightly more sophisticated version of the system that has two components. First, decides whether there is a polyp or not, and then tells you where it is in the image, draws a bounding box around. Now, when you have a false positive, if the system tells you, oh, I think there's a polyp in the image, you have to ask the system, where is it? And it's going to draw a bounding box. And then you can look at what's in the box and understand why you're getting a mistake. And we found out, for instance, that there were very often surgical instruments in the bounding box. So the system had learned that usually if there is a surgical instrument in the frame, it means there is a polyp, which of course is not correct. But now we can identify where the error is, and we can fix it by changing the training set and other things. So if you build a modular system, you encapsulate things, I think it's a very powerful technique for being able to interpret where the errors are and to compensate them. And there is much more, of course, but this is, I think, one key idea.
So let's press on that a little more. So do you think that, and I've heard sort of both sides of this debate with some of my colleagues at the Center for Data Science. Do you think that these connectionist architectures can really are suited to handle explanation, or do you think there's sort of a need to go back to some of the symbolic approaches to deal with it and somehow integrate the two?
So those are different questions. The connectionist architectures, the deep learning architectures, are opaque, and this is almost, it's inherent in this kind of approach, right?
I guess what I'm really getting at, and I'm sorry to interrupt, I just want to make sure I'm being clear. I guess what I'm asking is, to what extent can these systems really reason, right? So in the older days of AI, people were really hung up on building systems that could reason, and they would extract knowledge from humans, and then the emphasis really was on reasoning systems. And we've had this real shift away from that with data and learning and recognition and prediction. And we've sort of almost completely forgotten about sort of the other things that we used to focus on, such as reasoning and explaining and being able to introspect. So have we sort of gone really far in one direction and we'll see the other one building up, or do you think this approach can actually handle reasoning as well?
So I think that's one of the fundamental questions in AI today, is how do you combine the symbolic and the reasoning with the deep learning connectionist approach? One has to be aware of a few things. First of all, it is possible to do everything in a neural way because that's what the brain does. So I do believe that you can implement reasoning, symbolic stuff using neural networks. We don't know how to do it well,
right,
but we know it's possible.
Right.
That's the first thing.
Right.
And maybe artificial system will do it slightly differently, because you can have a symbolic system that is not neural and combine it with a neural system for perception, for images, etc. So we will see down the road in the next few years. It's going to be very interesting to see which approach is going to be the most efficient, whether to do everything in a neural way or whether to have mixed systems that have lower levels that are neural and higher levels that are symbolic. Now, if you look at the brain, it's very interesting to see that if you think of the human brain as having evolved over the last million years from the state of being a chimpanzee, essentially, language, the symbolic stuff, is very recent. It's the last 100,000 years. So most of our brain is doing not symbolic stuff, actually. It's doing vision, it's processing things, it's controlling our body, and all this stuff happens automatically. We're completely unaware of it. We're completely unaware of the algorithms that are taken. And the part we're aware of, our language, our consciousness, the symbolic part, is a very, very thin layer that has appeared very recently in the last 100,000 years.
It's interesting. This sort of reminds me of just one. This just reminds me of someone said that our initial approaches to intelligence were based on logic because we thought that's what makes us intelligent. And I think what you're saying is that that's kind of a retrospective thing that we've imposed on things. All right.
It's a late invention.
Yep. Great. So I think that's a good time to ask Philip to join us for the town hall.
Interesting.
So actually, this is a good segue. I'm curious to know what you think about this. The last topic we've been touching on. Pierre is saying that the existence proof is humans do it with a neural net, so we should be able to do everything.
Yeah, I think perhaps an analogy to today's neural nets are more like kind of the back of your retina, or the sort of very, very early parts of the image processing system. And there's actually some biological basis to believe that. People have taken retinas out of animals, bathed them in oxygenated fluids, showed them patterns, and looked at the firing patterns. And so the first ones behind the sensors tend to find edges, which is very much what the low layers in the network are doing. And then higher up, you get textures. And I don't think we've connected the higher processing yet. We haven't figured that out. And it'll be different wiring, it'll be different algorithms. But there's an existence proof, I think, with humans. But we've just now started on the signal processing. And I think I mentioned this earlier, listening to sounds, some of the basic stuff's work. But, there's a little bit of, the expression fake it until you make it. Even though it's not really understanding, it's quite surprising how intelligent sometimes it seems
to be
in terms of what they can do.
All right, cool. So I think we should open it up for questions to anyone. The panel?
A law professor by the name of Eugene Volokh published a paper last month, I think it was, wherein he postulated how you would get to AI judges. And one of his basic premises was, it doesn't matter what happens in the black box as long as humans are persuaded that the outcome is one that they accept. Does it matter what AI does as long as humans are persuaded by what it does?
I think it does matter, because when you say humans are persuaded, there is always one human that will not be persuaded, There is such variety and diversity in the human race. So I think it is important to try to understand how things work.
But different things are important at different times. So for example, just using pattern matching, can you look at a pathology sample and recommend how that patient should be treated? For that patient, that's kind of all that matters. But if you're actually a scientist and you're trying to understand, hey, what's the underlying biological mechanism to help discover some new therapy that influences it? I think you have to get into a mechanistic understanding as opposed to a statistical understanding. So it depends on the purpose. So the FDA is faced with this. Like, if these things just work empirically, how can they block them? They need to approve them, but if we don't know how it works, it's very disconcerting. And you don't know how it's going to fail either. These systems fail in very strange ways. There's a great example where you have, a picture of a fox, and you can add a little bit of a high frequency noise, and it thinks it's a banana. So these systems have very, very strange patterns. They don't fail the way humans do, but it depends on the purpose. I think these things are going to be accepted for lots of practical purposes. So,
I guess my response would be that it really depends on the how much sort of signal there is in the problem, and the danger associated with trusting systems completely is that you just never know those edge cases that you may not have encountered, and so it's dangerous, even if the system has never made a mistake until now, and you generally tend to trust it. I think it's dangerous to just trust it. Now, the other side of the coin, and this is something I've experienced even personally, is that when a system never makes mistakes, you just assume that when you're looking at something, that it's right, even when it's wrong. You just sort of get lulled into this, sense of security that, it must be right, because it's never made a mistake so far. So that's what I see as the danger of accepting a system just because it's never made a mistake until now.
You had mentioned earlier that there's these two camps, the reasoning camp and then the statistical empirical camp. And one, I think, really interesting area of research is to bridge the two, is like, can we somehow add the priors from what we know mechanistically, and then add the statistical system to give the color, to give some of the subtlety. And I don't think that's really been cracked yet. Like, I have people on my team who are like purely statistical empiricists.
Yeah.
Like, forget the humans, just look at the data.
Yeah.
But bridging those worlds is going to be...
And I know that companies like Intuit are dealing with exactly the same problem, right? Their system, what they deal with is something very rule-based, right? Laws, conventions, all that stuff. They've got all this data about taxes being filed that they assume are correctly labeled, right? And then integrating these two is a real challenge.
Right. So it's both using the priors and then also extracting essentially the rules out of the system are both big challenges.
Right, exactly.
Mine's a simple question. How long did it take to program the solution to be able to solve the cube? Just that effort of learning to do that. How many man hours?
Well, there's different issues. The learning itself, once you figure out how to do the learning itself takes about 2 weeks using a few GPUs.
So what did you learn from that exercise? I mean, I asked you that earlier, and you didn't. I don't know if you answered it or whether I just forgot what
I learned from the Rubik's Cube?
From solving this Rubik's Cube thing. What were your insights?
Let your students free. Do not interfere with your students. Don't try to manage graduate students. Let them free. That's what I learned.
Well, going back to Go, there was actually some very, very interesting learnings from the game. So just as one example, humans tend to want to win by a lot. And the Go game just knew it just had to win by one. So it was doing what people were calling slacker moves. It seemed to be extremely conservative, but from the program's point of view, okay, if I lock up this territory and lock up this territory, again, winning by 1 and winning by 50 were the same thing, Ted. And so humans are learning, hey, maybe we were playing too aggressively. It discovered like new lines of attack that no humans had seen. And there was a wonderful interview with the Chinese champion who, if you go back to IBM and Deep Blue, they just beat up Kasparov. It was a brilliant technical work, but we didn't learn anything new about chess from what Deep Blue did. It just executed perfectly. And we're learning a lot of new things about Go, and this Chinese champion was fantastic. Like, his life is the game, and he's like, okay, now I can learn new things that I've never seen before. So this is one of the hopes. My team does a lot of applying this to science, and like, can we lead scientists to new hypotheses, new ideas, see things that haven't been seen before? So I think this is like the first time the machines have seemed to be able to do this. So.
And my question is not so technical about AI, but more about you as experts, how you see the impact on the economic tissue. I mean, eventually, like, if you, instead of talking to tenure professionals today, if you are talking to middle schoolers, for example, what your advice will be as far as what kind of jobs, or, will the education system even be ready for this new generation to prepare them for the type of job that will exist in the future based on AI? And will there be kind of a gap, at some point with, the disparition of jobs that are, that will be replaced by technology like AI, but then we will need to be prepared and educated to do other types of jobs. So from your perspective, since you're in this world, like, how do you see this, and when is this kind of going to happen? Are we talking, 10, 20 years? I mean, I'm just curious to hear your perspective on that.
Well, you're asking us to predict the future, and that's a very, very dangerous thing to do. But my view is that it's a long process before AI will be solved. And along the way, there's going to be hiccups. There's going to be periods where some particular classes of people will have trouble in the workplace because they may lose their jobs, etc. There will be new jobs created. So in this transition phase, there will be all kinds of changes. But asymptotically, what maybe you can imagine is a world where there is much less work for everybody and much more of other stuff that we need to invent.
So let me just take a different stab at that, because I was in a panel a few days ago up in Bloomberg in Midtown Manhattan, and it was AI for millennials. So there were lots of millennials in the room, and one of the panelists had said, "You guys should learn how to code," and I totally agree with that. That's everyone these days should learn how to program. And then someone got up at the back of the room and says, "Well, what about philosophy? Shouldn't people be studying philosophy?" And I said, "Absolutely. I mean, everyone should be studying philosophy. I mean, you should know how to ask a question. A fool with a tool is still a fool. That you should be able to, ask a question and compare A and B and reason about it and argue about it." And I think essentially what it does is just sort of raises the bar for us as humans, right? We just need to get smarter. We just need to get, educated. And the data part and the programming is kind of, that's the price of entry now, right? It's almost like you need to be literate, but it doesn't really eliminate the need for sort of traditional, liberal arts education and philosophy. So that was sort of my response to a similar kind of question, but somewhat differently motivated.
I mean, even just going back to our retina work, you think, it's not like we're replacing doctors. By doing this automated screening, what we're finding is that the doctors are doing less of the kind of road work, but we're finding more patients just very earlier in the disease. So the doctors are actually doing a lot more. They're just dealing with patients who they can actually help because they're not already blind and they're lasering their eyes. So, it's definitely a shift. If your job is a very rote, just doing something that can be automated, it's going to get automated. But human appetites are infinite. And I mentioned earlier in my talk, are we going to bring back house calls? This might be a whole new job of visiting chronic patients at home. That's how we move the cost curve. So I think there'll be a lot of new jobs created. There will be differences, but we're not running out of appetite for.
Philip, if you'd been here last year, you would have known that we actually featured a company called Heal, which is doing house calls as we speak.
And
it's sort of an interesting. But let's thank the panelists for a fantastic time.